Okay, so we're going to go over sockets as our last element. But in order to go over sockets, we have to talk a little bit about network programming. This actual presentation comes from another class in which I do teach network programming, servers and so forth. As a result, um, there's a lot of slides here, but we're not going to go into deep detail on each of those. I just want to give you a flavor of some of the things we need to know about sockets in general in order for us to do it. Do we need to know everything about socket programming, network programming? No, we're going to create very simple sockets. We're going to do some very simple things in our class. We were going to mimic a real server that gives us the time back, but really not much more than that. But we do need to talk about some network concepts in order to make some of this stuff work. So that's what we're going to do. So we're going to discuss basic terminology, communication paradigms, protocol layering, and so forth. I'm going to go very quickly through these things. I'm going to explain what we need to know from a socket programming point of view and not much else. The reason for that is we do need to know a little bit about these things so that we can have some basic understanding of them. Because when we create sockets, we can actually create a variety of sockets, and we should know what we're doing when we're doing it. So we're going to talk about the important elements of network layer, including addressing and the transport layer, including protocols and port numbers. We're discussing compare application protocols and introduce the standardization of protocols. I actually go very quickly through this. I'm only going to do it just quickly enough so that you have a flavor of what happens in those things. But realistically, we want to just going to briefly touch on what a protocol is and then why we need a standardization process. Then we're going to talk about network programming architectural models, including client server and peer-to-peer. We're going to focus on client server, of course, but we're going to discuss a little peer-to-peer as well. And then finally, we discuss general networking applications. Again, this whole slide set is not going to be actually presented in total. We're just using this slide set as a means for discussing this stuff. Okay. So what do we mean by network? Two or more computer hardware resources are connected via a computer network. When we say computer hardware resources, we actually mean a CPU, memory, and some sort of I/O device, right? So it's got to at least have that when we think about computer hardware resources. Every machine on a network is what we refer to as a node. Node, which is our actual computers, are often called hosts. But a node could be a router, a switch, anything in between that actually provides us with a connection. Every node or host has an address, which uniquely identifies it to the rest of the network. Everything that is identifiable in the network is considered a node, and so it must have a unique address. Some addresses have names. This identifies an address and makes it easier for humans to use. We'll talk a little bit about this later. But for the most part, our addresses are not names. More terminology, most modern networks are packet switched. Data is essentially broken into packets. Packets are managed separately. Packets contain addresses to and from. That's all we really need to know about packet switch network from this perspective. You can go into your networking classes and get more details into how it actually works. We don't really care about that. We do care about protocols. Protocol is a precise set of rules governing how two computers communicate. Think about format of addresses, messages, right? As well as the order in which they're exchanged. If you write a client server application in which the server is expecting input from the client and the client never gives that input, no actual progress will actually be made, right? Essentially, you'll get a deadlock situation. So not ideal. So we need to know quite a bit about protocol in order to make some connection and make the client and server work together. This is really beyond the scope of the class, but we really want to think about it in terms of the order of exchanging messages. The actual messages that get exchanged are all part of the protocol. Now we're going to use very simple, protocol in which a client connects, gets a date, and then disconnects, right? So pretty simple network application, but this is very important. Why? Let's suppose you're waiting for a date on a new line, right? And the date comes back in just a format with a string with no new line character. Then the client's going to still be waiting for more information to come across when the server believes that that it's given all the information that it needs, right? So again, deadlock, right? This is pretty common problem. And so it's managed through understanding the protocol of the two interacting parties. So this is actually quite important. And we'll talk a little bit about this when we do some of our client server stuff. Two basic communication paradigms. We have a connection-oriented, where we establish a connection, and one in which we have a connection list, where there's no established connection. Connection-oriented, we form a connection. Server and client know about each other, and then they send and receive data over the connection. At any point, either side can terminate. Both sides will know that the connection was terminated, and you can guarantee bandwidth. You can guarantee certain restrictions with a connection-oriented, where you can't do it with connectionless. Connectionless, on the other hand, is we form a packet of data and we just send it to the network. Each packet would then travel independently, and each packet would have a notion of the destination and source, and each packet could be a different size. Obviously, the maximum packet size is fixed, but and we can talk about MTUs, or maximum transferable units. We don't really care about that. It's essentially each packet can be a different size, can be small, can be large, whatever, and it's received on the other end. Why so many protocols? Communication is actually really, really difficult to figure out, very difficult to understand, very, very difficult to work with. So what do we do? Excuse me. We have many sub-problems. So what do we have? We have hardware failure. The systems could fail at any given time. Networks can get congested, right? How do you deal with a network congestion? If everything's going through one superhighway type situation and everything has to go through it, it's going to be slow, right? That thing can get congested, which causes slowdowns. Packets can be delayed or lost due to the hardware failure, network congestion, and all those things. They can be corrupted. Data in transit actually is copied and pasted over and over and over. One way to think about it is it goes through one device, goes to another device. It gets copied from buffer to buffer to buffer. At some point we can get some data corruption. We could be reading it wrong. Who knows? And of course, because of hardware failure, network congestion, packet delay or lost, we can end up with data duplication. We end up in a situation where the sender sends a packet which just gets there late, but the packet was resent because it had not gotten the acknowledgement. And so we get a duplicate packet, right? So we have all these different problems. So how do we deal with them? Well, it's divide and conquer, right? All of computer science is focused on divide and conquer. So we divide the problem into pieces, we solve the sub-problems separately, and then combine into an integrated whole. The result here is what we refer to as layered protocols. Separates protocol functionality. Each layer solves one part of the communication problem intended primarily for protocol designers. This set of layers is called a protocol stack. We're going to go over this gently so that you have a core idea of how it works, and then very quickly go over sort of hand wave. You can take networking classes. You can take a network programming class. There's all sorts of options for you to learn more. However, we're going to go over this well enough for you to actually communicate with an external server. So TCP/IP model is the most common. It's also referred to as the DoD model. You have an application layer, and this is where the application layer does its application-oriented stuff, right? This is the stuff that's dedicated to the application. This is where the application protocol has its own, depending on the application process, has its own set of things that it does. So what does that look like? Well, it depends, right? HTTP works one way. SMTP works another way. Other protocols work other ways, right? So it's really important to know what those application protocols are and how they work, but that's not what we're interested in here. Okay. Underneath the application layer, we have the transport layer. We're going to talk about what the transport layer does, but it actually transports things from computer to computer, right? Wrong. This is the thing that handles the transmission from one application on one computer to an application on another computer, right? Imagine this is another computer, the transport layer communicates to another transport layer, and the idea is to hand it off to a different application, right? Computer to computer is actually the internet layer or the network layer. And this is actually handling from host to host. Remember, we talked about each addressable computer. That is what we're referring to there. Each addressable computer would have its own address, And the IP, ICMP layers are designed, protocols are designed to get the packet, get the things to that specific computer. The network interface layer is going from device to device, and it is how do we actually transmit actual data. The physical hardware is how do we read signals coming across the actual device, right? Do we have on, off, we have 8 cables and this is on, off, we have control and so forth. We also have what we refer to as collision detection. So we can have a shared medium, 2 sides. If both sides are talking, neither side is listening. And so this is the layer that handles that, okay? We are not going to focus on most of these things. I'm going to give a brief overview of each one's job and then call it good. I'm not joking. Okay, the network layer. We're definitely not concerned with the network interface or the physical layer, but we're going to start with the network layer. It's connection list, best effort delivery, no guarantee on order, the order of the packets that are received, whether or not they're delivered, and they could be duplicate. This provides what we refer to as machine-to-machine communication, from host to host communication. We have 2 problems here. We have congestion control and routing control. So congestion control is the number of packets in each network. Okay, now that we said that, we don't care anymore, right? We're not going to talk about congestion in any real way, but congestion is the kind of problems that causes order delivery duplication. Routing, what path is followed from packets to source to destination, is important. There are 3 basic components to the network layer. Only one we're going to talk about is the naming. We're going to talk about the IP address. The data structure of the packets, we don't really care so much. The algorithm, again, going to give a brief overview, and that's that. But routing requires a destination. Each source on a network must be addressable. So what does addressable mean? It means it has to have an IP address. And IP addresses provide this form of identification. It's a 32-bit binary value, and values are chosen to make routing efficient. That's its purpose. Address is always divided into 2 parts. You have a network part and you have a host part. The network part identifies the network to which the host belongs, and the host part identifies the host on that individual network. Now, we don't ever see this from a IP, 32 bits, 001 type thing. We generally represent each octet, each 4 or 8-bit component in a decimal form. So 192.168.0.23 is how we'd represent an IP address. This is how humans use it, right? The system is going to use it too, to some extent, but we use it this way because this is the human readable IP address, right? This is how we interact with IP addresses. IP addresses are actually 32-bit numbers. They work the same way as the octets, but they're 32-bit numbers. So how do we divide things into a suffix and prefix? How do we know which part's the network ID and the host ID? It's not as easy, right? The original scheme used notion of classes, so the net ID was to be exactly 1 or 3 or 4 bytes long. It's very problematic. We're not going to get into that, but the new scheme uses what we refer to as sitter, which allows for subnetting concepts. The net ID can be any number of bits. Great. So if the division is arbitrary, how do we determine where the division occurs? Which part's the net ID and which part's the host ID? Well, we have an address mask. And this is also known as a subnet mask. And the goal of a subnet mask, or the address mask, is to identify where the subdivision occurs. So we send a pair, address and mask, whenever exchanging route information, and this is known as the sitter block. Now, we never get into subnetting, we never get into these type of things, but when we do IP addresses, we do need to know a little bit about IP addresses in order to make some of this work. We're not going to communicate over a long haul network, those type of things, but I do want to give you some ideas of how this actually works. Sitter notation, addresses are written usually with a number followed by an M. The number, of course, is the IP prefix, and the M is the address length. So for example, your IP address could be this, your subnet mask could be this. So I'd write 192.60.128.0/22. You can also identify the subnet mask as being 255.255.252.0. Now, I'm not going to go in detail here, but the subnet mask is all 1s until we get to all 0s. All the 1s identifies the host part, the 0s identify the, where the 0s would be the host part. And where the ones are, identify the network part. Pretty simple. We're not going to go in detail here. We don't need to. But this is difficult. What is the IP address, if you guys know this, for Google, right? Most of you would not know this unless you've had to do some coding. You had to do some network applications, right? You've never actually done this. You probably never known this, but this is a very simple IP address for a DNS server for Google. It is 8.8.8.8. It's easy to remember. It's an easy test address for you to use other to test whether or not addressing is working the way we need it to work. But that's the only easy address I can remember, right? If I want to go to chase.com, so in order to pay my bills as an example, how do I get there, right? I go to chase.com. That's not an IP address. That's what we refer to as human address. Those are symbolic names. These are designed to remain the same even if we change the numeric address. And they have to be unique for each host on the network. This requires an infrastructure, which we refer to as the domain name system. This translates symbolic names like chase.com to an actual IP address. DNS implements a distributed database of name to address mapping for lookup. Do we need to know how this works? No. Okay. I'm going to show you some ways of doing an NS lookup just on a computer so that you can see it when we do the demos, but we don't need to know how it works or why it works. It just allows us to use local IP addresses, right? Or translate names to IP addresses. Okay. Note DNS also refers to the actual infrastructure, not just the distributed database. It actually refers to the infrastructure system as well. All right, transport layer. This provides end-to-end communication from application program to application program. This is what handles reliability, flow control, applications here, protocols here are TCP and UDP. So reliability goes into us talking about, I'm trying to remember where it is, order, delivery, and dealing with duplication, right? That's our reliability. We know what congestion is, right? You know, you've ever traveled on a car in a highway, you know what congestion is, trust me. But what is flow control? That means essentially that the speaker is speaking too fast or too slow for the other end. Yes, you're overwhelming the other end with too much data, so we can slow the other person down. That's all I mean. Differentiate host applications on the same computer using what we refer to as port numbers. Servers listed on ports, client connects to those ports to use servers. Yay! So let's look at UDP versus TCP. TCP is connection-oriented. It's the notion of a virtual circuit. It guarantees delivery in order. It also requires you to connect, and once you connect, you can transmit data back and forth. UDP, on the other hand, does not require connection, so you're just sending packets. You're collecting data and sending packets. Delivering order is not guaranteed. If you wish to maintain that, you can do that. Now, why do we have UDP if we have TCP, right? Don't we always want the data to get across? And the answer is actually quite simple, right? Sometimes we need everything, right? An email message as an example. In an email message, you have to have the full email address in order, in all of its glory, in order for it to make sense. You really do. But if you're watching a streaming video, as an example, you might be fine with losing a packet here or there, as long as you got most of the packets delivered and they're in order and so forth, right? But losing a few packets here and there is not that big a deal in a streaming application, whether it's audio, video, or whatever. And so that works out really well. If you have that kind of service. But a couple things, when you have that kind of service, you have to manage delivery, order, duplicates, and all those things. Usually duplicates are just discarded. Usually order is not guaranteed, right? So if it's out of order and we don't care about it anymore, whatever. But you have to manage those if you want to. That's why it's particularly good for streaming services when you have massive numbers of things coming in, and losing one or two things is not a big deal. Okay. But when you have to have a message like, you know, our time server is an example, you connect to the time server and that whole packet either comes through or it doesn't, right? It's very important to have that connection. So Most of what we'll be doing in our demo space will be actually TCP, but just so you know what the differences are. More on ports. Server ports are considered to be well known. Why is that important? Server ports need to be well known because you have a large number of clients and one server typically. So all those clients need to know how to get to the server. Duh, right? That's why server ports are generally well known. The port number 80 for HTTP, the server listens on port 80 and waits for a request. Client ports are not well known. They're generally temporary. It's used to actually connect to a server. If the app needs to reconnect, it just requests a new port, right? Duh. Now, client ports are generally used the range 1024 to 65, 535. Operating system handles the request. There's no guarantee of having a certain number unless you ask for it. If you're asking for it, it's very likely a server port that you're asking for. We rarely create a specific server. But it depends on, again, the application. But again, when we deal with clients, client ports are what we refer to as temporary. And so they're just used as the other side of the server port. Okay. Network applications run on end systems. They depend on the network to provide a service, but can't actually run software on the network elements. Network applications typically run on multiple machines. They are separate computers, separate processes, separate everything. Different end systems communicate with each other, and software is often written by many different people. So we often need to explicitly define a protocol. Types of message, like what kind of requests and responses are we expecting? What about message syntax? What are we expecting the format of the message to be? Not only the type of requests we can get, the type of responses we should send, but what are the message fields and how are they separated and so forth, right? Then you have the semantics of the field. None of this is trivial, right? Semantics field. What does the information in those fields actually mean? And you go, wait, what? Like, what does name mean? What does this mean? What does it mean to the processing or the request or the response and so forth? All that has to be thought of ahead of time. And then rules for when and how a process sends messages. This is the order and what we call the tango. I call it the dance. I call it the tango. Both sides have to explicitly expect certain things to happen. For example, a server waits for things to happen. A client sends a request and the server sends a response, as an example. That's pretty typical for a client server. But remember, if we send a request and the server's not expecting to send a response to that request, the client's just sitting there hung, right? So it's really important that the order matters as well. So we'll talk about comparing application protocols. I really won't spend a lot of time with this. Don't really care. So commands and replies. Telnet send commands in binary where most protocols are text-based. The actual, Telnet, mail, web, all those things. Data types, Telnet, SMTP, and ASCII all use standard, Telnet and SMTP always transmit text data in standard ASCII. SMTP actually uses a MIME standard for sending non-text. HTTP actually incorporates some of that. But what I want to talk about briefly with the MIME text, I'm not going to go in detail because this is not the class, but what essentially the MIME standard does is translates the data, the non-text data, into text. We won't go any further than that. Telnet, FTP, SMTP, and HTTP all depend on reliable transport protocol. Telnet, SMTP, and HTTP frequently use a single TCP connection. We don't really care about that. I don't want to spend time on that, but just give me a quick overview. Telnet SMTP, the server retains information about the session. If, for example, HTTP servers are completely stateless, right? There's no connection. They connect, they send their request, they get their response, and then they disconnect, right? There's no HTTP servers do not have a notion of state. In Telnet SMTP, they do. FTP has a directory, and so technically it does as well. So reflecting on these, protocols are tailored to the application, of course. Each protocol is customized to a specific need. The Tango, the order in which operations occur, depend on the operations that need to happen. And so, of course, that happens. Protocols have each many key similarities. Each new protocol is influenced by previous ones. New protocols generally borrow from older ones. And that's true if you're developing your own protocol. If you're developing your own protocol, look at what HTTP does. Look at what SMTP does. Is your system similar to that? Steal. That's what they're there for. Protocols generally rely on some underlying substrate. So TCP, for example, DNS in some situations. Relevance of the standardization process. So we don't actually go into detail on this. And the reason why I'm not going to is pretty simple, but the basic idea is that imagine web servers. I like web servers specifically. So with web servers as an example, you have many different vendors of web servers, right? So you have Apache, you have IAS, just to name two big ones, right? Then you have a large number of browsers, and those are clients, and they all need to connect together. It's not acceptable for it to sort of work for some and not work for others, right? They all need to work. So obviously a standardization process came in early on those. And the big network protocols for internet processes such as SMTP, NTP, FTP, all these guys are standardized protocols, so you can connect to it via any application protocol, any application that uses the correct protocol. All right, so network application design, network applications generally follow a series of architectural models, and it's not a variety of them. It's three basic ones: client server, peer-to-peer, and hybrid of the two. Client server is obviously the most common one, especially for the systems programming world. Where we're going to spend most of our time is looking at server client. And what does that look like, server client? That looks like you have a client that sends a request to the server, and the server processes and responds to those requests. That is it. It is not complicated, right? Very simple. Client server should feel like you're at a hotel, not a hotel, that you're at a restaurant and somebody walks up and asks for a drink. Server says, do you have the money for the drink? Right? It goes through its Tango, and then the processes the request, and then the client moves on their way, and the server waits for the next request, as an example. Pretty simple. That's basic core functionality. Peer-to-peer is where you have no specific server. Everybody's kind of acting like a client and server, but there's no uniform person in charge or system in charge. A little bit more complicated. We see this in streaming services. We see this in a variety of places. This isn't relevant to us, but peer-to-peer is, I'm trying to think of the word, has distributed control. Client server really has, the server has most of the control, centralized control, where peer-to-peer has decentralized control. And then hybrid system is some connection, some variation of the two of those. Right? We won't get into detail because we don't need to here. Client initiates a request and server fulfills the request. Pretty simple. Imagine going to a bar and ordering a beer. Basic model: server starts first, waits for contact, client starts second, and initiate the contact. Server responds and then goes back to waiting for another contact. Pretty simple. Characteristics of a client. Arbitrary application program becomes a client usually temporarily. Can also perform other computations while it's waiting for the results from the server. It's invoked directly by a user. This is the part a client typically runs for the user, and then runs locally on the user's computer. Actively initiates contact with the server, and usually contacts one server at a time, right? It contacts the server, then it may contact another server, may contact another server, whatever. That's its general purpose in life. Yay! Server, on the other hand, is a special purpose. This typically has privileges that the client does not, right? The client often asks the server to do things because the server has privileges. Special purpose privileged program. It generally provides one service. If you end up with a server that's doing 2 or 3 things, that's usually a very big security fail. So you generally want to do something about that. So we typically have each server has one job, and it does its job very well. Servers typically handle multiple remote clients simultaneously, right? Threading. Invoked automatically when the system's boots, usually a daemon. It executes forever. It's designed to sit and wait for requests. So it sits there and waits forever. It waits passively. It does nothing until being asked to do something. It waits passively for client contact. It accepts requests from arbitrary clients. Needs powerful computing and operating system. Remember, when we deal with 1 or 2 requests, not a big deal. Any computer can do this. But when we deal with hundreds of thousands or million requests, we need a powerful computer and operating system in order to handle those things. All right, we discussed basic terminology, communication paradigms, and protocol layering. Remember, this is not designed to be, I'm trying to think of the word. This is not designed to be exhaustive or complete. It's designed to give you enough information so that when we talk about creating sockets and we talk about connecting 2 things, that we have a basic understanding of how this overall works. Okay. Then we talked about the important elements of the network layer, including addressing, what an IP address is. We talked about a little bit about sitter. We don't need to know that much about sitter. Just need to know that sitter works that way. Hopefully we can avoid it almost completely. And then we talked about protocols and port numbers. Protocols and port numbers don't seem to make any sense until you actually see a port number in operation. Pretty simple process, but when you see it in operation, it's okay. But remember, we can have 2 servers running on the same computer. Which server is the one you want to connect to? We can identify that via port number. We discussed and compared application protocols and introduced this. I don't really care about that as much. We talked about network programming architectural models, including client server and peer-to-peer. We really didn't talk about peer-to-peer, or definitely didn't talk about hybrid. And then we discussed general networking applications, the characteristics of a client, the characteristics of a server, and so forth. There is another part to this, but we are done with this part. If you have any questions, please make sure you ask them. This is just preparation for getting us ready for the discussion of sockets. All right, thank you guys. I'll see you at the next presentation.